Hi, welcome all of you to this particular presentation on high-speed power reconfigurable power electronic controllers. I am Ajeesh, working with the CDAC Thiruvananthapuram in Power Electronics Group, and this is a recent development of us regarding the control aspects, the hardware design for control of power electronic controllers. So we call it as HSRPEC, high-speed reconfigurable power electronic controllers. So normally in control system or power electronic control system, we are designing the control system using analog components like op-amps, resistors, capacitors. For example, the control system elements are PI controllers, adders, integrators, subtractors, etc. In analog control system design, we are designing with the resistors, capacitors for the and op-amps for the integrator, differentiator, all the things. As you know that the inherent disadvantage of analog control system design, they are bulky in nature and they are actually affected with the component drift, etc. So after that, we actually using digital due to the advent of digital signal processors or simply processors, we are then designed the control system using digital signal processors and the microcontrollers. And in that techniques, we are actually used the software programming technique and logics, some logical thinking and numerical methods to design the control system for power electronics or any process control system. In designing such a control system, the major point is about the DSP. Industry like power electronics actually found some difficulties with the present DSPs, so that I will explain later. When you design a control system in a DSP, the problem with the DSP is that today you start designing a control system with a DSP, digital control signal processor. Within 2 years, the component will be obsolete, or the you are not able to get the power, digital signal processor from the market. Normally, a power electronic system actually takes a minimum of 5 to 10 years to stabilize. During that time, the control system components are obsolete. So that is a big problem with especially in dealing with the railways, military systems, etc. So also we know that most of the digital signal processors are actually meant for the wireless industry, so that some of the logics actually does not require in the digital signal processors, and also it is very difficult to find out a digital signal processor that is best suited to your application. So with that in mind, we actually developed a new reconfigurable control architecture for power electronics and power system. So that what if I have a processor so that the user defines instructions, internal modules, speed, memory, etc. So that means the power electronic design engineer actually going to design the processor, the pins, and he can use his design as long as he wants. That means simply an obsolescence free design. Power Electronics Group of CDAC, we actually developed an FPGA based power electronic controller, so that the internal modules or the processor, even we can insert a processor inside the FPGA with some user defined instruction, internal modules, speed, memory, etc. So that the user have 100% control over his control system design, and he don't worry about the obsolescence of the processor. So we actually developed the technology based on SOPC. SOPC means building embedded system into a single programmable integrated circuit like FPGAs. So in FPGA we can design a complete embedded system which includes processors, which may be soft or hard processors, memory means RAM and ROM, intellectual property means some off-the-shelf intellectual property core, IP cores, and custom hardware blocks, which is suited for the particular application where the user is actually intended to use the power control processor. So in a summary, we can say SOPC is how all or majority of the components on a single programmable chip like FPGAs. We actually have some experience with the following customers, especially with the Indian Railways and defense application. The life of a locomotive for the railways is around 10 to 30 years. And the industrial power electronic system, maybe the life is 5 to 10 years. Average life is 5 to 10 years. So that there won't be any change in the control or any part of the system. Normally, processors used in such cases, in such customers are obsolete within 4 to 6 years, and even we have a substitute for the new previous processors. The next generation processors actually which call for software porting overhead according to the processor and hardware change, which essentially requires some redesign in the board itself. So that will actually call for some difficulties with some of the industries. And a solution for this is a use soft processor IP cores in a general purpose FPGA that will solve, so that at any point of time with the minimum change in the hardware or a zero change in the hardware, he can modify the processor or the control system design. And this actually calls for a single chip solution. Normally we know that it is very difficult to find out a power electronic or a processor with all interface or required for his application. For example, in railways, multifunction vehicle bus is a particular bus standard used for railway application, and it is very difficult to find out a processor with a multifunction vehicle bus. In that case, what exactly is people are using? They are using some ASICs along with the digital signal processors, which actually calls for a complex design. If we have a processor that is having a multifunction vehicle bus, then it is better. But it is very difficult to find out such a processor. But for a solution to this is, you don't require to change the FPGA or the FPGA, the hardware, and you can use some soft IPs of the MVB controller, and that you can easily attach to the FPGA design. And single core to multi-core design. So at some point of time you understand that with the single core or the single processor what you have used in your application is not good for your rest of the application. In that case, you have to change the processor to multi-core, or you have to use some other processors along with the control processors. In that case, from single core to multi-core, normally in a DSP environment, we actually require a hardware redesign, maybe require a hardware redesign with increased cost. But in this architecture, same FPGA hardware, you can use it for single to multi-core application. That will not call for a hardware change. Hardware means the physical PCB change. One of the reasons why the DSP obsolete so fastly is that the major portion of the DSP income is from wireless application. Around 62.4% is from wireless application, and in the automotive, actually it is only less than 5%. So which exactly include our power electronic application. So that the wireless application is changing fastly. So that's why the people, the DSP designers are not ready to keep the other processors, because they have a more income from the wireless application. In this architecture, using parallel processing, so we are actually using parallel processing of parallel processing using hardware blocks than software pipelining. So which the hardware implementation of a control algorithm will take less time than the software counterpart. Control blocks in dedicated hardware to perform functions faster than a CPU, like PI controllers, filters. You can use a hardware module inside an FPGA. Normally, inside an FPGA, the hardware is designed using HDL languages. So a PI controller HDL format, which will actually convert it into a hardware block inside an FPGA, that will perform more faster than the equivalent software design. And C to H compiler. C to H means the C language to hardware, which is a few features of the FPGA design tools normally, which actually inspect the C code. Normally the application code contains some C code, and the compiler will try to convert it into equivalent hardware implementation. And we know that hardware is actually performing faster than a software. Comparative studies from a third-party agency said 8201 Neos 2 cycle is equivalent to 24603 Tiger Shark cycle, where Tiger Shark is so this is actually tested with a standard FIR filter algorithm. In that, the majority portions of the filter algorithm is implemented in hardware along with a soft core CPU. Neos is a soft core CPU, and which is taking only 8201 cycle, and which is working only 200 MHz, whereas all the modules are written in software language like C or assembly, which is running on a Tiger Shark application taking this much cycles. So where the Tiger Shark is working with the 600 MHz, where the soft core processor Neos 2 is working with 200 megahertz only, and better time to market criteria, because so which this type of design actually improves the time to market criteria, because the same FPGA board, once you manufacture a board, particular board in a generic fashion, then you can use the same board for different applications. For some application it may be a process control processor, and for other application it may be a drive control chip. And we proven CPU core and IP set actually will give you better time to market criteria, and which handles a wide variety of applications. And higher reliability is another advantage of this type of development. High level of integration and resource utilization in a single FPGA, and board design is also simple. The on-chip, the FPGA is coming with some industry standard bus protocol like Avalon, AMBA, AXI. The board design is simple, and the internal PLLs, so that the on-chip, inside the chip, the high-speed digital circuits are inside the chip, and on the off-chip or on the PCB, actually we have only the low clock speed circuits, so which reduces the EMI, so that the PCB can be smaller, consumes less power, and easier to get through EMC test. And board testing, and for testing the board, dedicated board testing design can be loaded into the FPGA without making any disturbance to the control application or the actual application code. That is yet another advantage of this type of methodology, SOPC methodology. So now we look into the conventional control design. For example, we will take a motor control application where we actually use a DSP or microcontroller unit for implementing most of the control algorithm, and of course A to D converters is for the analog to digital conversion, and some digital outputs is for PWM input, and then we are feeding that to the power stage, and the motor is from the motor we are actually taking the feedback to the processor, where in the present scenario we are using an FPGA board which actually used to support the DSP to increase the number of PWM channels, or to implement some dedicated glue logic purpose. Assume for an industrial controls power electronic system, maybe it required to communicate with some other power electronic system through some industry standard, like for example an Ethernet. In that case also we require a communication board which is made of FPGA or microcontroller or application specific processors. So this is the present design trends in power electronic system. And if you take the resource utilization of each processors, you can see that only 60% of the DSP resource is used, and rest of the 40 is not used. And where, because maybe we does not require rest of the 40% for the particular application, and only we can see that only 10% of the FPGA logic is used, and here also we can see that only 20% of the FPGA resources, FPGA or microcontroller resource is used for the communication purpose. So we can see that most of the time the FPGA or the 90% of the resource inside the FPGA is free use. If it is possible to use that 100% resource inside an FPGA, then it is reconfigurable, since FPGA is a hardware reconfigurable device. So within that concept, we actually developed a SOPC controller architecture which contains a soft CPU, maybe it is soft or hard CPU inside an FPGA, and the HDL motor control logic, space vector, or the power electronic specific modules are also a module to the CPU, like PWM generators and the ADC interfaces. So everything is on an FPGA. So the communication part is also on the FPGA. The interface required to communicate with the Ethernet is also FPGA, so that we can save the board design from this to this one, a simple board design, which is almost all the control system is designed inside the FPGA. So based on that, we actually developed an SOPC based power electronic controller board version 1.1, which is having this much of specification. So FPGA is, we actually developed a generic control board, so that for any control system which requires up to 56 numbers of IOs, you can use this board. So this is an adequate number for an industrial power electronic control system. So this board is actually designed over a Cyclone 3 FPGA, and we have some stack connectors for this one. So this is actually act as the processor for your control system, and this board structure is fixed for the application to application. The hardware inside the FPGA is reconfigurable and the IOs are configurable. So without programming the FPGA, this is a simple board, and which is having only an FPGA and the required peripherals to for the FPGA design application in configurable fashion. So we actually developed a technology to program the FPGA in a reconfigurable fashion for power electronic applications. So that once we program this for a drive application, then we can say that this is a drive controller chip, or if it is for a DC-DC converter application, then we can call it as a DC-DC converter chip, like that. So the advantage is that there is no fixed IOs here. The user can use, let us say, the pin number 5, I can use it as an ADC interface, or pin number 10, I can use it as a PWM. So the user can define which pin he has to use. So also for interfacing with the real power electronic system, we actually developed a peripheral interface card which is targeted for DC-DC converter application and some AC drive application, and front-end converter, MPPT, solar MPPT applications, etc. So which is having this much specifications. So custom design for the specific power electronic application is possible with this, and this is we actually targeted for this type of application. Only thing is that you have to provide a housing for the SOPC, this control board. Control board, what exactly we developed. So now in this slide we will see how to configure this for a different power electronic application. For example, we can take a high performance drive. So this is a drive application we used for railway purpose, whereas you can see that a front end rectifier and an inverter for the speed control application. The rectifier so once you consider the control system architecture, there will be a rectifier control and inverter control, and in railway application there is an MVB controller is required. MVB means the multifunction vehicle bus, which is the bus standard or the communication standard used in railway application. So keeping that in mind, we will see how can we configure this. So for the inverter control application, normally we are using the speed sensorless speed control technique. In that we are not actually measuring the speed, instead the voltage and current which is flowing through the motor is measured, and from that that is feeding to the motor dynamic model. The motor dynamic model actually estimates the flux and the speed of the induction motor. So in a DSP based environment, these things are actually designed using C language, and the instructions inside the language is executing in a sequential fashion, whereas in this architecture we actually developed a motor dynamic model. Like a multiplier in a CPU, we can attach to the CPU, so that once you read the voltage and current from the ADC, you can directly feed that voltage and current to the motor model, which is actually a hardware module inside the FPGA that actually directly within the next cycle itself it's directly estimate the flux and the torque command required, speed or torque command required for the application. So once you implement this in a DSP architecture, it requires some 15 to 16 or more than 25 lines of code that will execute in a sequential order, whereas in this architecture within single cycle, the next cycle itself, once we have the voltage and current from the ADC by the processor, then the next cycle you just feed it to the motor dynamic model. It will automate the next cycle itself. The motor model the motor dynamic model estimates the speed and the flux or the torque and the flux required. PC architecture, this is designed in a hardware description language, and we call these as IPs, intellectual property cores. So this is the board inside the FPGA. Earlier we have seen this board. This board there is an FPGA. The FPGA is configured for that particular application, where we have the PID controllers, which is used for the control system application, and the interrupt controller PWM, the motor dynamic model, the phase transformations. So these are the power electronic specific modules required for the application, and there is a CPU which exactly the major role of the CPU is to coordinate the activities of different IP modules. Different IP modules means the PID controllers, interrupt controllers, external memory interfaces, and the communication protocol, the data conversion interfaces. So that, for example, the CPU just to read the voltage and current from the ADC A to D controller, A to D converter, and directly feed that to the motor dynamic model to get the speed estimation. So basically speaking, the CPU have only a job, that is just to read data from a memory or an external device and give it to an IP core or the power electronic specific IPs, so that only memory operations for the CPU core. That will actually helps the CPU, which is performing faster than an equivalent DSP implementation. So the control blocks are now the part of a CPU. They are the hardware control blocks. The PID controllers are not a software module, are part of a hardware module. So this is actually we configured for this drive application, the indirect speed control application. So other similar PI application can also do with the same FPGA board without any redesign. That means, for example, for a DC-DC converter application, we does not require the motor dynamic model. You can just remove that model. Then we can use other modules for the DC-DC converter application. That means that calls for the advantage of reuse. And these modules, like in a multiplier in a CPU, you can call this module with some instruction that are called a custom instruction, and the user can define the instruction or the function what exactly he intended. So we will show some example for that custom instruction later. And similarly, you can configure it for a DC-DC converter application, and the same FPGA you can use it for multi-core application. For example, earlier we have seen in this application there is a rectifier controller and inverter controller. The same FPGA board, with the same FPGA board, what we have here, the same FPGA board, you can have 1 processor, 2 processor, 3 processor or 5 processor depending upon the logical capacity of the FPGA. Multi-core design is possible without any change in the FPGA or FPGA board, and you can also put some custom logic inside which does not require any intervention of the CPUs. So here I have shown a DC-DC converter application in core 1 and an inverter control application in core 2. Processors in FPGA. Normally, FPGA vendors support for soft and hard CPU cores. Soft means processors are implemented in VHDL, Verilog, etc., and can be downloaded into any FPGA hardware. Examples of some soft core CPUs are Neos 2, Microblaze, ARM Cortex M1 are some of the examples, and these are highly reconfigurable. That can be downloaded into any FPGA. Some are vendor dependent, but more than 20 soft core processors are available. Leon 3, S1 Core, ARM Cortex M1, DSP UVA 16, and these can be downloaded into any FPGA. These are and we will get this as a schematic or a code-like software. Once you have that code-like software with you, and you can use it for n number of applications. So you don't worry about the processor obsolescence, because it is available as a HDL code or a schematic structure that you can download it into FPGA. So this actually solves the processor obsolescence risk. And to prove the technology, we actually used Neos 2 softcore CPU from Altera Semiconductors. So, and these have a flexibility from 20 MHz to 430 MHz depending upon the FPGA what we have used. So these are some of the features of the Neos 2 CPU what we have used. And the power electronic processor system, what exactly we designed. So we have a softcore CPU. Upon that, which may be Neos 2, Microblaze, or Leon 2, Leon 3, S1 core, whatever be. This is only a softcore CPU. This is having the arithmetic logic unit and some of the bare minimum processor peripherals. And upon that, we are adding the flash interface, the communication or the debug ports, JTAG UART, and the system ID that is used for the software protection of your design. Upon that, we are actually adding the power electronic IPs, what we designed. So we actually designed 18 power electronic specific IPs like PWM, PI, timers, A to D controller, etc. So this is the architecture of the power electronic control system or the power electronic processor what we actually designed for the power electronic applications. It's a reconfigurable thing. So suppose you, for one application, for a particular application, you does not require a PA controller, you can remove that one. So for Neos 2 processor, the best specification used is Avalon, and for AMP processor it is AMPA best specification. That is the only requirement for designing the power electronic IPs. That requires only a small change in the top level entity of the power electronic IPs, and that does not call for a huge or a complex programming. It requires, only thing is that the top level entity of the power electronic IP what you design should meet the specification of the processor bus. That's all. And you can all dedicate a protection logic without any intervention to the CPU. That is yet another advantage of the power electronic processor what we designed. Assume the current through an IGBT is going up from the permissible limit, so that you want to immediately protect, you want to immediately turn off the PWM pulses to the IGBT. In that case, in normally DSP based environment, normally we are using an A2D controller interrupt. Also, you can add the protection logic without any intervention to the CPU. Normally in a DSP based environment, suppose a current in an IGBT is going up, the particular channel in the ADC is measuring that current. So normally for disabling the PWM, it requires a CPU intervention. So which actually requires some 10 or 4 or 5 cycles of the CPU. But here, without any intervention to the CPU, the A2D controller can directly turn off the PWM module by putting a simple logic here, so that does not require any intervention to the CPU. So that this means that suppose the current through an ADC channel is rising up, the protection logic can independently detect that current, and that can turn off the PWM. On the next cycle only, the CPU will understand that the PWM is turned off due to some due to the current shoot up in an A2D controller. Before that, the actual power system or the power electronic system is protected. So this is another advantage of this type of design, so that the user can insert in the hardware architecture of the processor. User can insert some protection logic or custom logic required for his own application. So we actually developed 18 power electronic specific IPs required for the power electronic application, and the control blocks, for the requirement is the control block should be designed in HDL, then only we are able to port it into an FPGA based environment, and the functionality and timing should be properly monitored using test benches or IP verification. And it is but actually it is a time consuming process, but it is only a one time process. So the technology developed are the power electronic IP libraries, power electronic specific, which contains power electronic specific IPs, and design procedure for the IP developer. That means the one who is actually developing the power electronic specific modules, the PA controller, PWM module, etc. And drivers for the power electronic IP libraries. That is the custom instruction which is required to access these IPs through an application code through the software CPU. That are called the drivers for power electronic specific IPs, and the design procedure for SOPC user, or how he can use the high speed reconfigurable power electronic controller in a power electronic system. And the SOPC controller card, that is the card which we actually developed for there is the small card we developed for the controller application. SOPC interface card, that is suited for some AC drive, DC-DC converter, photovoltaic applications, and the power electronic, some power electronic application evaluation report based on the SOPC technology. So the custom instruction, another powerful features of this type of design is the custom instruction or custom function, so that the user can add some his own instructions or modules to the power electronic or the custom IPs what he developed. So these are fixed instructions. So that means for an IP he developed an instruction. He can use it for any software CPU with the same instruction and the same IP. And these are simple and easily understandable. For example, for the PI controller what we developed for instruction or function, custom function for the power electronic PI controller. So that hardware input PI means this is the address of the PI, which PI you are using, and the KP and the KI values, which means that we are actually inputting the KP and KI values to the PI controller. This is used to enable the PI controller, and this is used to input the error to the PI controller, and this function is used to get the result of that instruction. So once you put the data into the PI controller, there won't be any software running in background. This PI controller is a hardware module, and that will accept the error data, and based on the KPKI value, it will, the next cycle itself, it will calculate the output of the PI module. So that means it requires only single cycle to execute this instruction to this instruction. Whereas in a DSP based environment, you require minimum 10 to 15 lines to line of C code or line of assembly code to execute this PA functionality. So, and we can see that any power electronic engineer can understand this instruction, which means that the software code inside the application code is less and they are easily understandable. So, good readability is one of the advantage of the custom instruction or custom function, and the number of lines in the instructions are in the application code is very less, and which because the application is or the power electronic functionality is in hardware environment, which actually execute very faster than equivalent software instruction. Also, once this is the instruction what we develop, if a user want to change the name of the instruction or the function, he can easily edit the instruction also. That is also possible with this type of environment. So technology deliverables are soft processor core integrated control design procedure and the user manuals, hard HDL control libraries like PA controllers, filters, PLL, PWM, phase transformation, etc. There are 18 power electronic specific IPs, and application evaluation report using SOPC controller card what we developed, the voltage mode control of DC-DC boost converter, AC drive, variable voltage, variable frequency AC induction motor drive, we on single core and multi-core processor, and FOC, field oriented control of induction motor, and SI as an HIL, hardware and loop simulation in FSS miniature, and the details are available in the NAMPET, National Mission on Power Electronics Technology website, nampet.in. So the development activities is here. First, in the host PC, we are actually developing the hardware configuration, and that can be downloaded into the control board what we develop. Then this is the FPGA configuration that are actually going to download. That means this is the processor actually going to download into the FPGA. Then we can write the software module, and we can that we can use it to verify, or we can directly put into the power electronic application. We have some examples of the DC-DC converter control using SOPC controller. So here I am going to show some of the evaluation results of the power electronic application, some power electronic application using the SOPC controller what we developed. So this is a DC-DC converter controller, and this is using the voltage mode control of DC-DC boost converter, which exactly require a PI controller and a PWM module. So the required peripherals are power electronic peripherals are dragged into the configuration, and of course it requires a serial ADC controller and a serial DAC controller to visualize the results, some of the signals. So, and here we used a NEOS2 processor core system, and this is the DC-DC controller chip actually developed in the hardware project. So the PA controller is now as a hardware module. PA and the PWM is a hardware module to the CPU. Like an assembly language, he can, like a multiplier in some other processor, he can simply call the PA controller using this type of instructions. And we benchmarked the result with the TMS320F2812 processor. The boost converter control algorithm actually takes 6 microseconds for one loop completion, whereas the SOPC controller actually taking 800 nanoseconds. Then for an AC drive application, so this is the lab setup what we have assembled. So this is the block diagram of the variable voltage, variable frequency, or the V/F control of induction motor. So this there actually requires a alpha beta to ABC, 2-phase to 3-phase transformation. So this actually we designed it as an IP module, not as software C code, and is attached to the CPU. and we got a good results. So that the main loop execution time for this application is only 2 microseconds. So the same architecture we designed with the same board, with the same application, we actually designed the tested the application with the on two processor core on the same FPGA board. So the boost converter control in one CPU core and the inverter control is in other CPU core. So like this, the processor 1 is for the boost converter control and the processor 2 is for the inverter control, and there is only everything is inside the single FPGA. So this actually took only 1.5 microseconds. So whereas the single core actually took around 2 microseconds. When we put this into a multi-core environment, which is actually taking 1.5 microseconds, here you can see that there are two CPUs. One is for the boost converter and other is for the inverter control for the induction motor. So these are and FOC in SOPC. So we also tested the FOC in SOPC as a hardware and loop simulation. And the red blocks are actually in hardware IPs. The main loop execution time is only 10 microseconds in 100 megahertz. SOPC architecture, whereas in a TMS320F2814 processor, it is taking 22 microseconds with a clock speed of 150 microseconds. So the design flow is actually like this. So we have the soft core CPU. Upon that, we are actually embedding the power electronics specific IPs and the required IP modules for the control application. For the communication interface, we can use JTAG, on-chip memory, some microprocessor peripherals like the system ID, and some parallel ports, parallel IO, and the power electronics specific IPs along with the custom instruction. So the higher level of design reuse, which means that one IP you design for a particular application, the same IP you can use it for any other application if you develop the IP cores in a generic fashion. And reconfigurability, the same FPGA board you can use it for a particular application, and that can be reconfigurable for any similar type of power electronic application without any change in the hardware or without any change in the IP core set. Only the execution or the order of the order of the control algorithm is changing. And the reduced processor obsolescence risk, that is one of the best advantage of this type of methodology, because the software CPU, the soft CPU, the IP modules, everything is available to you as a text file, so that you can use it for it. Everything is available to you as a text file. As long as the text file is as long as with you, the processor obsolescence risk is, or the component obsolescence risk is bare minimum. And don't worry about the FPGA obsolescence, because everything is designed by you as an HDL module. HDL is an FPGA independent language, and simplified design update or change. So lesser overhead in control software design means the application software looks like a very simple because of the usage of custom instruction. At any point of time, the user can easily edit, or any other person can easily edit the control instruction what he used in the program, because the program looks simple. And parallel processing, of course, use of multi-core processing, we can reduce, the same FPGA board, you can convert it into single core or multi-core environment, so that the parallel processing is possible in this environment. Of course, improved time to market, because the generic FPGA board is with you, the proven FPGA board and the proven CPU core is with you, along with the power electronic specific IPs, that you can use it for different power electronic applications, so that within bare minimum time you can design the control algorithm and you can test easily, which calls for improved time to market. That is means, but in a DSP based environment you require some dedicated programming, and you need to read the data sheets of the new DSP actually what you use, and you have to study a lot about how to configure the program inside or configure the hardware modules inside the DSP. But in this case, once you familiarize with the IPs, then as long as the IP cores with you, you can develop your application program within a minute, I will say within a bare minimum time. And single core to multi-core flexibility, the same FPGA board you can use it for single core to multi-core application. So this is all about my presentation.